In this lecture, we are going to learn the directional derivatives and gradients of functions with three variables. And then we are going to talk about how to find minimum and maximum values. So first, directional derivatives and the gradient, which bring us the directional derivatives. You have seen this, but in functions with two variables. So now f is a function of three variables, x, y, z, and same thing, we pick a point, x0, y0, z0, and then you look at that particular point, you pick a unit vector, which is a direction, ABC, and then the directional derivative of our function, so pretty much is how the value of our function f is changing along the direction ABC. Is this directional derivative with direction u of function f at the point x0, y0, z0. Okay, the directional derivative in direction u of function f at the point x0, y0, z0 is you go to the point x0, y0, z0. Then you go along the unit vector u or the direction a little bit. So you go a little bit, h. Okay, so here is the a little bit. You go on top of your original point x0, y0, z0, and then you look at the value, how much it changed. Then of course you make the limit. If the change is so infinitesimal, so small, h approaches 0, the change of the output over the change of the sort of how much you go along the vector. That's our h. Okay, if the limit exists, that is our directional derivative. And then similar to the two variable case, the gradient vector del f, which is f partial f, f partial y, f partial z, sort of give us the projection on each axis of the directional derivative. Then for any vector, we can just sort of add the effect on each coordinate together. So you do inner product of del f and the unit vector. Now, if you look at two function with two variables and function with three variables, you can sort of think x0, y0 is a vector x0. And then u is the unit vector, then you are really just adding. So here's the origin and your x0, y0 is here. Well, the point is here. I don't want to use x0 anymore. So this vector is x0, and you go along the unit vector u a little bit, and you'll see. Okay, so you can use the unit vector definition, which is like covers both function of two variable or three variable or actually more variables in one equation, in one definition. And also the directional derivative equals the del f, the gradient, dot the direction unit vector. Also, it's true for both 2 or 3 or 4 or 5 dimensions. First example, we are pretty much doing the same thing but with three variables. Find the directional derivative of function f, which is x times sine yz. Well, again, here I meant y times z. Then take sine. At the point 1, 3, 0 in the direction of 1 to negative 1. So, of course, we are going to use the fact the directional derivative in the unit direction u of f at whatever point equals the del f dot u. Okay, that's the definition. Well, that's the formula. So we need to first find del f for a general form. That is f partial x, f partial y, f partial z. Look at our formula. Take derivative with respect to x. Sine yz is the coefficient of x. Take derivative with respect to y. X is the coefficient. Then you are taking derivative with respect to y. Well, I'll write the parentheses. Yz. Then you are taking derivative with respect to y, which means you differentiate this, the input, and you get z. Last, take derivative with respect to z. X is the coefficient. Then we take derivative on a sign, which gives us cosine. And then the derivative of the input give me differentiated yz with respect to z, so that's a y. And then I'm going to, well, let me rewrite it a little bit. I don't like my y and z at the end. So again, yz together is the input. Then I have xz cosine yz and xy cosine yz. Now plug in my point 1, 3, 0. I'm going to have sine 0, x is 1, z is 0. Well, it doesn't really matter what else, but cosine yz will be 0, and x is 1, y is 3, cosine y times c is 0. So I'm having sine 0 is 0, and 1 times 0 gives you 0. 1 times 3 times cosine 0 is 1, so only the z component, we have a non-zero number 3. Now go back to the vector. Our vector is not unit, which means we need to divide its length, which is 1 squared plus 2 squared plus negative 1 squared, and that gives me 1, 4, and 1, which is radical 6. So our unit vector u will be 1 over radical 6, 2 over radical 6, and negative 1 over radical 6. Then finally, our directional derivative in the direction of unit vector u of our function f at the point 1, 3, 0 is the inner product of these two things. So we are having 0, well, where is that little minus sign come from? 0 times, well, whatever, it's 0 plus 0 times the 2 over radical 6 plus 3 times negative 1 over radical 6. So pretty much that's 0, only this survives. I have negative 3 over radical 6. And that is the directional derivative of our function x times sine yz at the point 1, 3, 0 in the direction 1 to negative 1. What it means? When your function f, when your x, y, and z are at x equals 1, y equals 3, z equals 0, if you add a little bit, add x, y, z with the proportion 1 to 2 to negative 1 on top of your original value 1, 3, 0, and look at the output, the rate of change is negative 3 over radical 6. If let f be a function of differentiable function of 2 or 3 variables, the maximum value in the directional derivative is the del f. Because you are multiplying a directional derivative, okay, a unit derivative, and it occurs when the vector u has the same direction as the gradient value del f. So what it says is the directional derivative is the largest, or the direction that your f changed the largest at this point is the gradient direction. So if your vector goes along fx, fy, or three variables fz, that is the largest possible direction that the function is changing. Okay, now let's look at the example 2. Find the maximum rate of change of f of xy equals 4y square root of x at 4, 1, and the direction is in which it occurs. So pretty much we're saying let's find the gradient and let's look at the length of our gradient vector, because that is the direction and how fast the gradient, that is how fast the function could change. So this is a function of two variables. We have the del f equals fx, fy. Fx, I'm differentiating with respect to x, so the 4y is the coefficient, and I'm differentiating x, radical x, where x 1/2 power, so 1/2 x negative 1/2 is the derivative. And differentiating y, the 4 radical x is its coefficient, and differentiating y, you get 1. This will be, let me write it, I'm going to evaluate it, so I'm going to write it as a radical form for the x component. 4 times 1/2 give me 2, and then I have the y on the top, and then the negative 1/2. This is 1 over radical x, goes to the denominator. And then, well, the y component is just 4 radical x, and go. Then my del f at the point 4, 1 will be 2 times 1 over square root of 4, comma 4 radical 4. So this is 2 over 2, 4 times 2. So this is 1, 8, which is, by the way, the direction. We're looking for the direction it occurs, right? So that's the direction. And then the maximum rate of change is the length of our del gradient vector. Is square root of 1 squared plus 8 squared. So this is 1 plus 64, square root of 65. Okay, now you can pause the video and try practice number 1. Now let's talk about minimum and maximum values. A function has a local maximum if, like, this is the peak point of value. If at AB, the function is the highest near its neighborhood, okay, like in its sort of little ball around it or little disk around it. We don't care far away what happens, but in this little range, at this particular point, you have the highest f value than its neighbors. Then your f has a local maximum. Then, of course, the value of f at this point is called a local maximum value. Similarly, if this is the lowest point in its neighborhood, then a function has a local minimum at the point, and the value is a local minimum value. So we say a function has local minimum or maximum at sort of the input side, but the local maximum or minimum value is the output. A point is called a critical point. Okay, this is a very important definition. A point is called a critical point if either both of the partial derivatives is 0 or one of these partial derivatives does not exist. So you need if the partial derivative exists, you need both of them to be 0. But if one of them does not, you don't need both of them not existing. One of them does not exist, make it a critical point. Then why are we talking about critical point? Because that's where our local minimum and maximum value will happen. You have a local minimum or maximum, then the point is definitely a critical point. The reverse is not true. Not all the critical points will bring you a local minimum or maximum, but the local minimum and maximum will only happen on, the critical points. Now let's look at our next example. We're going to find our local minimum and maximum values of this function x squared plus y squared minus 2x minus 6y plus 14. So how do we find local minimum and maximum values? We find where they could happen. Where could they happen? They happen when your f partial x and f partial y equals 0, or you can't find them. You can't find either of the partial derivatives. So fx is x squared give me 2x, y squared 0, minus 2 from the 2x, negative 6y and 14 are all constants. So my f of x is 2x minus 2, and my f of y is x squared give me 0, y squared give me 2y, negative 2x give me 0, negative 6y give me negative 6, positive 14 give me 0. You found these two derivatives, and the critical point happen when both of them equals 0. So you have 2x minus 2 equals 0 and 2y minus 6 equals 0. Well, they don't really have anything to do with each other. You just solve each of them. 2x equals 2, x equals 1, 2y equals 6, x equals 3. I meant y equals 3. So that's your point. Your critical point is 1, 3. Which means at 1, 3, you could have a local minimum or a local maximum, or neither. Now let's look at our function one more time. We have x squared plus y squared minus 2x minus 6y plus 14. This is a circle-like function. It's not really a circle, but if you complete this perfect squares, what do I need? I need plus 1 here. So plus 1 minus 1 here, plus negative 6 divided by 2 squared, plus 9 minus 9 here. So I'm having x minus 1 squared minus 1 plus y minus 3 squared minus 9, then plus 14. So x minus 1 squared plus y minus 3 squared. I'm minusing 10 plus 14 plus 4. So when x equals 1 and y equals 3, they are both 0. The two perfect squares are both 0. And when your x and y are not 1 and 3 at the same time, they will be a little bit bigger. So that tells me that my 1, 3 is a local minimum, because when your x and y are not 1 and 3, the f value will be greater than 4, because at least one of the perfect squares won't be 0, which means positive. And this local minimum value is, you plug in your 1, 3. This will be, actually plugging in this will be easier, but I'll do the original. Plus 3 squared minus 2 times 1 minus 6 times 3 plus 14. Because in the future, you won't have this nice form tell you why you are having a local minimum or maximum. You will see what I mean. So 1 plus 9 minus 2 minus 18 plus 14. This will give me 10 minus 2, which will be 8, minus 18, negative 10, plus 4, plus 14, 4. Okay, and this is my local minimum value. I have one local minimum value, which is 4. But as you can see, it's easy to find a critical point, but it's hard to decide what kind of critical point you are having. Is it a local minimum? Is it a local maximum? Is it neither? That's where we need our next theorem. It's called the second derivatives test. What it says is, if you have both f of x and f of y being 0, which is the first kind of your critical point, okay, not the not existing kind. If f partial x and f partial y are both 0, then we can decide whether it gives you a local minimum or a local maximum or neither by computing this thing. There are second derivatives, okay, fxx, fyy minus fxy squared. What it is? It's actually fxx, fxy, fyx, fyy, given that, they are the same. So maybe that's easier to remember. It's really a matrix, and take determinant. So if you compute d and you get a positive number, if our d is positive, you are guaranteed that you are getting a local maximum or minimum, depending on whether f partial x is positive or negative. If your fxx is positive, you are getting a local minimum. If fxx is negative, you are getting a local maximum. Okay, it's sort of like your concave up, concave down case in 2 dimensions. And then when you are having d less than 0, it's not a local maximum or minimum. So here I have this picture where, this is a local maximum, this is a local maximum, this is a local minimum, this is a local minimum. But there are points like here, like this point, if you look at its left and right, it's the lowest, but if you look at its front and back, it's the highest. This kind of point were here. Okay, when you are looking at its left and right, it's actually the highest point. But if you look at its front and back, it's actually the lowest point. These kind of points are called saddle points. Okay, so this one is also a saddle point. D less than 0, you get saddle points. If D is greater than 0, fxx will tell you whether you're having a local minimum or maximum. And if D equals 0, our test doesn't work. It could be anything. Okay, so our test fails when D equals 0. But when D is not 0, it tells you what it is. Let's look at our example 4. We're looking for the local maximum and minimum values and also the saddle points, if you have any. The function is x4 plus y4 minus 4xy plus 1. So, of course, we are going to compute f partial x, for x third, x to the 4th power, gun, minus 4y, plus 1, gun. And f partial y will be x to the 4th power give me 0, taking derivative, y to the 4th power give me 4y third, minus 4x, 1 give me 0. So I'm actually having 4x third minus 4y equals 0, and 4y third minus 4x equals 0. Or if you divide by 4, x third equals y, and y third equals x. how are we going to solve this? Well, you sort of have x ready or y ready, whichever you want to plug in the other variable. I guess I prefer to keep x, so I'm going to get rid of the y by plugging in y equals x to the third power in my second equation. So y actually is x to the third power, then to the third power equals x, which means I'm having x to the ninth power minus x equals, well, let me slow down. X to the ninth power equals x, or x to the ninth power minus x equals 0. Factor it, you have x to the eighth power minus 1 equals 0. This is a difference of squares. X4 minus 1, well, plus 1, x4 minus 1 equals 0. Another difference of squares. So x4 plus 1, x2 plus 1, x squared minus 1 equals 0. Another difference of squares. X times x4 plus 1, x squared plus 1, x plus 1, x minus 1 equals 0. Zero product property. X equals 0, you can solve. X to the fourth power plus 1 equals 0. Not happening, because x to the fourth power is, well, a square at least, right? So it's non-negative. Plusing 1, it can't be solved. X squared plus 1 equals 0, same reason. X will be positive and negative 9. We are not allowing complex numbers. X plus 1 equals 0 is solvable. X minus 1 equals 0 is solvable. You have negative 1 and 1. These are our x values, and y is x to the third. So 0 here, negative 1 here, and 1 here. The three critical points you are having are 0, 0, negative 1, and 1, 1. Now let's work out our second derivative test. So we need fxx, which is 4 times 3x squared, 12x squared. Fyy is 4 times 3y squared, 12y squared. And fxy is negative 4. Then my d is 12x squared times 12y squared minus negative 4 squared. This is 144 x squared y squared minus 16. And you look at each of the points. When x equals 0, 0, x and y is 0, 0, your d is plugging 0 and 0 here. You will have 0 minus 16 or negative 16. Right? Negative saddle point. 1, 1. Oh, negative 1 is the first. My d will be 144 minus 16 equals 128. Positive. Then you need your f double x. That's 12 times negative 1 squared. Positive. This is a local minimum. And the value will be f negative 1 equals negative 1 to the fourth power plus negative 1 to the fourth power minus 4, negative 1 plus 1. I'm trying to manage all my writing here. So this is 1 plus 1 minus 4 plus 1, which is negative 1. Okay, local minimum value, saddle point. And finally, you have 1, 1, where d will again be 128, and fxx is again 12 because you are squaring them, right? So your f11 will plugging in be another negative 1, but another local, well, because this is greater than 0, minimum value. So we got one saddle point and 2 local minimum values, but no local maximum value. Okay, now you can pause the video and try practice number 2. Finally, I have a remark. If f is continuous on a closed bounded set, what it means is it has a boundary and the boundary is included in your set, in your domain, D. Then f attains an absolute maximum value and an absolute minimum value at some point. Okay, if you have a closed bounded set, which means again, it's sort of like it has a boundary and the boundary is part of your domain, then at some point f will has an absolute maximum, which means a value that is higher than every other value on D, higher than or equal to. And also similarly, you will have the absolute minimum, which means you can't find another value that is higher than this. Okay, so the absolute maximum and minimum will be realized at somewhere, and the extreme values will happen. So the maximum and the absolute maximum and minimum values will happen on 2 possibilities. A, critical points. The local maximum and minimum are your candidates, but also the boundary is your candidate. So to find an absolute maximum or an absolute minimum, you do what we did before in example 4. You list all the local maximums or list all the local minimums. Then you look at the boundary and see how function, what is the maximum value on the boundary. Okay, and then you compare them, see which actually has the higher value. That point wins. It's easy to say, but actually it's a lot of work when you involve the boundary, because the boundary could be described differently, and like you have a rectangle, then you have 4 sides, you need to try each of them. So I'm not going to do that, but just letting you know that is like the game plan. You find your local maximums, then you look at how function works on the boundary, find its maximum, or maybe find the maximums on each sort of, say, a rectangle. Maybe each line segment give you a highest point for f, then including the other, say, 5 local maximums, you compare which one wins eventually, and that is your absolute maximum value. Similarly, you can do the same thing with the minimum values. But again, I'm not going to show you an example of that because it's super long. Okay, that's it for this lecture.